We'll get started here in about 5 minutes. Thanks for your patience.
Oh, I see. Oh,
Recording in progress.
We'll get started in just about a minute. Thanks for your patience.
What? It's raining.
I don't know what's wrong with me. I still feel so.
All right, everybody. Thanks for joining in this afternoon. So I'm going to go ahead and share my screen. Could somebody unmute and let me know if you're seeing the course homepage now?
Yep, looks good.
Thank you very much. All right, so this class is being recorded, and after class is over and I get the video captioned, I will post the recording in the announcements. If you've noticed, I've been posting the recordings from our sessions in the announcements, along with any other important items. Last week, I did talk about the project. So if you weren't here, You can watch the video from our class meeting. Also, I do have a video that discusses the project. It's all the way at the bottom, but it's there. If you wanted to, go ahead and take a look at that. And also, just as a reminder, I made available some extra resources that you could use. And there's a link to them in the announcements. And I've been also sharing that whenever I post the videos. So again, the announcements are pretty important. So you should take a look at them, periodically to make sure that you aren't missing any important material. All right, so I'm going to go into the weekly overviews, because the weekly overviews, as I've said several times, contains the information regarding each week's assignments, the materials that you need to read or review to help you prepare to complete the activities and assignments, as well as the objectives for the week. Okay, so you can see here this week we're taking a look at Newton's laws. We'll be furthering our understanding of motion. In particular, we'll be looking at forces and the role that they play where motion is concerned. For this week, you have several activities and assignments to complete as well. So you see problem set number 5 is due by this Saturday, 11:59 p.m. And as a reminder, the problem sets lag behind a week, right? So problem set 5 actually deals with 2D motion that we covered last week. So last week, I lectured on 2D motion. You had an opportunity to complete a discussion on 2D motion last week, and now you will complete the problem set that relates to 2D motion this week. So you see you have a discussion on Newton's laws that relates to the topic that we're covering this week. I will talk about your first bonus assignment. And then, as with every weekly overview, there's a link to tell you how to submit the problem set. And if you're having questions, you can post a question in the class questions form. And, if one of your classmates wants to respond, that's fine. If not, then you can reach out to me and I'll be happy to answer your question. Okay? So again, the weekly overviews are very, very important. So notice also in this week's overview, there's some reading materials, the chapter 5 that comes right out of the textbook. So I've put that chapter here for you to read because that's what deals with Newton's laws. There's some videos and some other website, a NASA website in particular that relates to Newton's laws that you can take a look at. And then the supplemental notes, as I mentioned, those are my notes. Those are my lecture notes that I'm sharing with you, okay? So all of the other items are for you to investigate and ask questions. They're for you to use as you're working through the assignments. My lecture notes are also available for you to use, but I'm actually going to cover them. In addition, I always remind you that under useful links, there are some great tools that can be of use to you. There's some additional free textbooks, some tutorial websites, simulators. Please feel free to use them at your liking. Okay, so those are some additional tools that can help you as you move through the material in this course, right? But I put the items that you need for this week in this week's overview, okay? Any questions about that? There's one other thing that we'll talk about tonight after we're finished with Newton's laws. and that is the midterm. The midterm is actually next week, but it is going to open on Saturday. And so I want you to have the instructions that you'll be needing so that when it opens on Saturday, you can go ahead and get started if you choose to. So, after I'm done talking about Newton's laws and, we've addressed any questions that you might have on that topic, I'll spend some time sharing information on the midterm so that you are comfortable with how you need to proceed and you're ready to, start working on it when it opens on Saturday. All right, so let me go back into the weekly overview on Newton's laws. I'm going to go under required readings, viewings, and I'll open up these supplementary notes. All right. So as with every set of my notes, I always remind you on how you should be studying. And I'll focus on this for a minute because it is really critical at at this point in the course. It's been critical, but it's even more critical now because we are getting to the point now where all of the background on measurement, on 1D motion, on vectors, on 2D motion that you have been learning about in the prior weeks of this course are going to be utilized now, applied now, especially as we begin to look at forces. And so I say that, this is critical that you are, utilizing these tips here that I've provided you on how to study, because the material is building, right? And just like any building, if the foundation is weak, then you're gonna have, issues, right? So, I stress this how to study portion of my notes more now, because if you're missing some things along the way, or you're not sure, or things, you have some gaps in your understanding, is going to make things challenging. And so what I always say, if you have questions, you need to get those questions answered, because the more you let them linger, the worse off it is for you. Okay. So you see here, there are some objectives that I'll be focusing on in this packet. These objectives come right out of the weekly overview. You see, we're going to be looking at Newton's laws. We talked early on in this course about what is a law. A law is a particular pattern that has been observed and verified through experimentation over and over again, but is very limited in its scope. So see, we're going to be focusing on Newton's laws and how they pertain to forces and motion. You'll have to be able to look at a picture and identify various forces, and then utilize that to help you express the relationship between those forces in a mathematical form. That's what Newton's laws do for us. They help us understand forces and provide us the equations, because a lot of times laws can be modeled mathematically with equations. And so you'll have to be able to look at a diagram, identify various forces in that scenario, and then translate that into a mathematical formula or mathematical equation. We'll look at some different types of forces. You see they're talking about normal force. We'll look at what is normal force. We'll be talking about inertia and the role it plays in terms of motion. And then we'll be keying in on the idea of when are forces balanced and when are they unbalanced, and how does that impact the motion. And then finally, we'll be looking at action-reaction pairs and the role that they play regarding motion and the connection between these action-reaction pairs and Newton's third law. So up till now, we've been studying kinematics, right? We've been utilizing kinematic descriptions of moving objects, meaning we've been focusing on things like distance, position, displacement, speed, velocity, acceleration. But we have not been focusing on what the causes for those motion, what's responsible for the motion. We just know the object is moving, and we want to measure those particular types of properties like displacement and velocity and acceleration, which are vectors, and properties like time, speed, and distance, which are scalars. But nowhere in those kinematic descriptions do we focus on forces. And so when we start to focus on forces, when we add forces to this description, we focus on dynamics. And so when we study things from a dynamics perspective, then we look at the factors that cause and control the motion of the objects, okay? And so there are some key concepts that we have to understand. What are forces? What is mass? What is inertia? Because those things come into play when we're dealing with a dynamics description of our moving objects. And I always like to give you a little bit history background into these things, right? I focused before on the importance of scientists who laid the groundwork, if you will, in physics, right? And I mentioned Galileo in some of our prior lectures. But he's pretty important at this stage because he was like one of the earlier scientists to really look at motion from an experimental perspective. Now, he didn't get everything right, but the groundwork that he laid was important because where Galileo stopped, Newton picked up. Literally, you can see that Galileo dies in 1642 and Newton's born in 1642. So almost literally that, Newton picked up the torch and advanced our understanding of dynamics, of forces, and their impact upon moving objects. And because of the groundbreaking work that he did, that's why we give him a lot of respect. And you'll see that the laws of motion that we're going to be dealing with all stem from what Newton was able to synthesize regarding moving objects. And then we'll see after then we'll also see that there's some other stuff that he was really critical at helping us to understand, like gravity. And we'll be looking deeper into that as well as we move through the various lectures and the weekly overviews. And as I mentioned, you're studying Newtonian mechanics in this class. Newtonian motion as understood and explained by Newton, by Isaac Newton. And when you think about all the things that move in our environment, he is really, really influential and important to this work that you're learning about. But he didn't just focus on motion. Newton was quite varied in the things that he studied, things like light and telescopes. And he even helped to invent calculus to help him describe moving objects. So he wanted to describe moving objects using rates, but there wasn't math to really focus on that area. And so, along with Leibniz, they developed calculus, which is mathematically the study of rates. And you see here, one of his major contributions is in formulating the laws of motion, which form the basis of dynamics. Whenever we want to understand the role that forces play in influencing motion of objects, we go to, at a basic level, we go to his laws. Now, his laws don't cover everything, because when you get into the realm of small things like on the atomic scale and fast things on the order of light, you can't use Newton's laws of motion. You have to go to quantum mechanics, relativity, some other type of description. But there are so many things that are big and slow compared to the atom, compared to light, that Newton's laws are applicable to a great many things. So we don't have to get too complicated when trying to understand what is force. A simple definition of a force: a push or a pull. So you push a wheelbarrow, you push a lawnmower, you pull a rope. Those are, when you are doing that pushing and pulling, you're exerting forces. And so it's kind of intuitive, but sometimes it helps to, really focus on what we think we know and be clear about it. And that's the beauty of Newton, that he moved us beyond just mere intuition and helped us understand the behavior of forces from a mathematical sense. Okay. And so this science of dynamics, this portion of physics that he created that deals with motion, motion of objects, focuses on the forces acting on it, right? And since a force is a vector, we talked about that last week, forces, they have magnitude and direction. So add that to the list of properties that we can measure that are vectors. Some of the vectors you've encountered so far are position, displacement, velocity, acceleration, okay? And all of them have a magnitude, which we say they have a size. And we know that size is the number and the unit and the direction. And if you looked at the material on the vectors as you were supposed to last week, you notice that when we specify direction, we can do it in a number of ways, right? We can use a compass. We can use the Cartesian coordinate system because it has a two-dimensional grid with, positive x, negative x, positive y, negative y. We can talk about left and right, up and down, forwards, backwards. The main thing is that if you exert a push or a pull, it has to have an amount. How much are you pushing? And what direction are you pushing? So that means force is a vector. And sometimes you see boldface used to denote forces that, that are vectors. You sometimes see them represented using arrows, as we've done in our prior lectures. We talked about utilizing arrows to represent vectors. But we don't want to get too difficult in terms of notation. So we'll try to do this in the simplest way possible. But you should be aware that if you pick up a textbook and you're studying forces and you see that bold print, or you see arrow bold with an arrow on top of it, they're denoting vectors. So all the things that we can do with vectors, we can do with forces because they can be represented as vectors. We can add them together. We can subtract them. And we can have more than one force acting on an object. And then when we add or subtract those various forces, we get what we call, the resultant force. And when we use the mathematics to find the overall force, what we're actually finding is the resultant force, or another very important term when dealing with forces, the net force. So the net force is what you get when you combine multiple forces together. Okay? And another important concept is that, in the work that we do not focus on internal forces. We only look at the forces that are external to an object, acting on the object from outside of the object, okay? So we don't worry about the internal forces because we're not doing things on the atomic level here. And when you do, you look at, atoms, molecules, you're focusing on the makeup of a system, and the internal forces become important, but we're not doing that here. So external force acts outside and upon an object, okay? So we often say what forces are acting on the object. Free body diagram. So recall I mentioned that one of the things that you need to be able to do is look at an object and determine what forces are acting on it. Well, a lot of times to do that, a picture is a very helpful thing. And we call a picture that shows all the various forces acting on an object a free body diagram. So you see, you have a very simple example of a free body diagram on the right-hand side here, where you have two forces, F1 and F2. And you can see the length, the magnitude of those forces is indicated by the length of the arrow, and the direction of those forces is represented by the direction that the arrow points. So you see F1 and F2 are pointing in different directions according to this diagram. And then you use some type of scale to determine the actual magnitude. We call it, when we do stuff like that, we're doing a graphical kind of analysis, or to investigate the magnitude and direction of our forces. But a free body diagram is just meant to be a simple sketch, okay? And the other nice thing is that when the forces are acting on an object, we can imagine collapsing that object into a dot. So that little red looking dot where F1 and F2 are acting on, we don't know what that dot actually represents. It's some type of object. It could be a planet, could be a dog, could be a car, could be a person, could be a table, could be any object. So we collapse the object into a dot, and then we show all of the forces acting on that object by drawing the vector arrows according to some scale and pointing in the proper direction according to which way the forces are acting on the object. Okay, so free body diagram. It's a good visual tool, okay? And so that's some general background on forces. And now what we have to do, based on our understanding of what a force is, a push or a pull, then we can utilize that understanding to dig deeper into Newton's laws of motion. So he proposed 3 laws. And what those laws allow us to do is to explain and predict how forces affect an object. The dynamics, right? The dynamics, remember, means it takes into account the causes. And so, these laws came directly out of Newton's observations and insights, as well as the work of some other scientists like Galileo and Kepler, okay? And maybe you've heard this statement used in other contexts before, but Newton's the one who coined it. If I've seen further than other men, it's because I've stood on the shoulders of giants. You hear a lot of people say that, my success today is because I stood on the shoulders of, some great mentors, or, that kind of thing, right? That originated from Newton because he gave credit to the work that Galileo and Kepler did. We'll talk about Kepler in more detail when we talk about gravitation in the coming weeks. But you know, these laws of motion were built on the work that those two scientists did. We'll, as I mentioned, we'll be talking about gravity, and that, you know, if we take Newton's laws of motion along with his law of gravity, the universal law of gravitation, more specifically, then we kind of have a more complete dynamics system to operate from. Okay, but we'll get to gravity later. Now you do have some exposure to gravity because we've talked about the acceleration due to gravity on planet Earth, 9.8 meters per second squared down, right? But we're going to dig even deeper than that in the coming weeks. So Newton's first law of motion. So I'm going to read the first law of motion as it is. And then what we're going to do is we're going to try to get deeper into it, break it apart, you know, break it apart, put it back together, investigate some different ways that we can, you know, we can understand what Newton's first law of motion is telling us, right? So Newton's first law of motion. A body at rest remains at rest, or if it is in motion, it remains in motion at a constant velocity unless acted upon or acted on by a net external force. Okay. Now, I'll use a little bit different language because number one, I don't like the word body because it can, sometimes people misconstrue that to think we're talking about a person or something like that. So I like to use
I'm in a Zoom meeting, so I don't think there's a way to toggle the audio on her.
Please stay muted if you don't mind. Unless you have a question, you know, if you have a question, feel free to unmute and ask. All right, so as I was saying, you know, I read Newton's first law to you as it is, but I'm going to use a little bit different language because I don't like the word body. It's a bit too CSI for me. I like the word object. Okay, so an object at rest remains at rest, or if it is in motion, it remains in motion at a constant velocity unless acted upon by a net external force. So now let me pick that apart even more. Okay, so I'm going to break it down in two. Okay, an object at rest remains at rest unless acted on by a net external force. So one thing we can focus on in Newton's first law of motion are objects that are at rest. And I'm almost certain that wherever you're at, if you look around that space or the room, wherever you're at, you're going to see some objects that are at rest. At rest means what? Not moving. So Newton's first law says if an object is not moving, it is not going to move unless acted on by a net external force. Remember, net means what? What you get when you add up all the forces that are acting on the object. So if you have some net force, some net external force acting on the object, then it is not going to remain at rest. Okay. The second part of that, an object in motion remains in motion at a constant velocity unless acted on by a net external force. So if it is moving, it is going to keep moving with the same velocity unless it is being what? Disturbed or acted on by a net external force. Okay. So you see what Newton's first law established for us is that there has to be a cause, and that cause is this net external force. And if you have one, then you can change the velocity of the object. And then, you know, we know what change the velocity means, because that means you can change the speed, speed up or slow down, or change the direction, or both, right? But there's even another word underlying there, the idea of changing the velocity. We know that a change in velocity creates what? An acceleration. So Newton's first law established for us what must be available for an object to accelerate, this net external force. If you have a net external force, meaning if you take all of the forces acting on the object, add them up together, and you have something left over that isn't balanced, then you can make the object accelerate. Okay? So Newton's first law establishes for us the causes for acceleration, these net external forces. Okay? Now, a lot of students can get the idea that if the object is at rest, it's not moving, and you disturb it with a net force or an unbalanced force, then it is going to move. And that motion means it changes velocity or it accelerates. But the case that gets students a lot of times is that they don't think about the object that is already moving. We did not say that net forces cause motion. We say net forces cause a change in the motion. Okay? So if the object is moving, it is going to keep moving with a constant velocity unless you disturb it or it's acted upon by this net external force. And what does that mean? If it is changing its velocity, it is accelerating. Okay? So the causes for changes in motion or acceleration are net external forces. You see, this is where Galileo got it wrong. Galileo got a lot of things right, but the friction part of that he got wrong. But if you go even further back, Aristotle, because Aristotle thought that the natural tendency of an object was to come to a stop. But that is not an object's natural tendency. The natural tendency of an object is to keep doing whatever it's doing. If it's doing at rest, then it wants to keep doing at rest. If it's moving with a constant velocity, it wants to keep doing that motion with a constant velocity. And the only way you can change that is to provide an unbalanced or net external force. Okay? So this is where, as I mentioned, that whole business of friction kind of threw Aristotle and even Galileo to some extent off, because you know, we see objects that are at rest, you know, they won't move. You know, wherever you're at, those things that are stationary are going to stay stationary unless you push or pull on them. But you know, when an object is moving and it just slows down and comes to a stop, sometimes if you're not thinking critically, you'll miss the idea that there's friction involved there. And that is a force that is acting on the object, slowing it down. See, Aristotle didn't know that there was such a thing as friction. So he just saw things stopping and thought that's what they're supposed to do. Well, they won't do that unless you provide that unbalanced net external force. Okay. Inertia and the mass of an object. So sometimes you hear Newton's first law called the law of inertia. And while we have talked about mass just from a unit perspective, you know, the mass is a fundamental property. We use the unit kilogram in the SI system, but that was it. We really didn't get into, well, what is mass, right? And so now, as it pertains to motion, we're going to look at that in more detail. Okay, so inertia is the tendency of an object to remain at rest or in motion with a constant velocity. Inertia is the tendency for an object to keep doing what it's doing. And some objects have more inertia than others. So they give the example of a large boulder versus a tennis ball. I always like to think a large bowling ball versus a small tennis ball. Which one do you think is going to have more inertia? Which one do you think is going to be able to keep doing whatever it's doing, whether that's at rest or in motion with a constant velocity? Well, the larger object, because it has more inertia. And how do we know? Because we can measure its mass. Mass is a measure of inertia. More mass, more inertia. Okay. A formal definition that we get into is mass is the quantity of matter within the object. Okay. How much stuff is it made of? And we measure that in the metric system with kilogram. Right? So in physical science, we use the kilogram as our fundamental mass unit because we're dealing with larger properties and larger quantities of mass, right? And so they tell you here, another important aspect of mass is objects with greater mass not only possess a greater inertia, but they also apply a greater gravitational force upon other objects. So more mass, the more gravity. And we'll get deeper into how that works as we talk about gravitation. But they kind of alluded earlier that, Newton is really important because of his explanation of gravity and that idea of larger objects with greater mass, exerting greater gravitational force is something we'll talk about in the coming weeks. Okay, so now Newton's laws of force, Newton's laws of motion, those dynamics laws that relate to force have to take into account mass. Mass is one of those critical properties when we want to talk about motion. We have to take it into account. See, we didn't need to know about mass when we talked about acceleration, position, distance, displacement, speed, velocity, average velocity, average speed, instantaneous velocity, instantaneous speed. We didn't need to know about mass then because those deal with kinematics. But if we're going to talk about forces and the laws that govern forces, Newton's laws, we have to understand mass. So now, Newton's second law. So Newton's second law mathematically states the cause and effect relationship between force and changes in motion. Okay. So Newton's first law establishes for us what has to be present in order to change an object's motion. Newton's second law allows us to mathematically determine the amount of force that is present. Okay? So Newton's first law says no net force, no acceleration. Newton's second law comes along and says, oh, you have a net force. Let's figure out how much acceleration. And so we can do that because we can write Newton's second law in an equation form. F net equals mass times acceleration. Sometimes you hear that referred to as F equals ma. Okay? But truly, you should be specific and say it's the net force that can cause an acceleration. Remember, forces don't cause, net forces don't cause motion. They cause a change in motion, which is acceleration. Okay? And so that's what they're showing in the picture here. All right? So on the left, you have a force being applied. You can see the red arrow pointing to the right. And you can see the length of that arrow. And you can see in that particular case, they're doing like they're passing a basketball. We call that a chest pass, right? They're passing the basketball. And so they're exerting a force on the basketball. Remember, force is nothing more than a push or pull, right? And because of the amount of force that they're exerting on the basketball, you know, the basketball has a certain mass, a certain amount of inertia. You can see that that force produces, that net external force produces an acceleration to the right, A1. But now if we take that same amount of force and we apply it to the SUV, looks like some type of SUV vehicle, same amount of force, that vehicle has a much larger mass, M2, and therefore you're going to produce a much smaller acceleration, okay? So we can see here from Newton's second law that the amount of acceleration is directly proportional to the amount of net force. The net force gets bigger, the acceleration gets bigger. You can see from Newton's second law also that the acceleration is inversely proportional to the mass. More mass, smaller acceleration. Smaller mass, bigger acceleration, okay? Right. So as I mentioned before, we have dealt with gravity to some degree in this class, but very limited, in a very limited fashion, because we only focused on the acceleration due to gravity, right? That acceleration that an object that is dropped, pitched down or pitched up as a result of gravity only, no air resistance, right? And so we denote that acceleration due to gravity as minus g, because we're writing it as a vector. Remember, the negative sign in this case on the vector tells us that the acceleration of gravity points down if we assume up is positive, okay? And so we want to take a little bit deeper look at gravity from the perspective of forces. Not the most inclusive definition, but you know, a kind of a definition that takes into account that objects have weight. And where does this weight come from? So when we look at how much gravity pulls on an object, we say that gravity is giving the object its weight. So the amount that gravity pulls on an object's mass is what is known as the object's weight. Okay? So to get the object's weight, we take the object's mass times the acceleration due to gravity. Remember that minus sign is telling us direction, right? So we know that an object's weight is pointing down if we choose up as positive, right? But there's some other important things that are being reflected in this equation. W equals minus mg, where W is weight, which is a force, and M is the mass, and G, minus G, excuse me, is the acceleration due to gravity, or the acceleration that the object feels. So writing this weight formula is actually applying Newton's second law to an object. So F equals ma, W equals m times minus g, okay? In addition, if we go back and think about our vectors and scalars, m, which stands for mass, is a scalar because it's an intrinsic property and it doesn't have a direction. So your mass is a scalar, it is location independent and the same no matter where you go in the universe, provided you don't, get burned to a crisp in a supernova or something like that, right? But, all that kind of stuff aside, your mass is the same no matter where you go in the universe. Your weight, however, is a force and therefore a vector which is location dependent. And it depends on the gravitational field minus G. Okay, so no matter where you go, Moon, Mars, Earth, Jupiter, Saturn, wherever, your mass is going to be the same. But as you move about the solar system, for example, your weight is going to change. On the Moon, you'll weigh substantially less than you do on Earth. On Mars as well. If you go to Jupiter, you're going to weigh substantially more because the acceleration due to gravity on Jupiter is more. Okay? In other words, Jupiter is so big that it can pull on you a whole lot more than the Earth can. All right? If you're on Jupiter. All right? So weight, that is a force on an object that shows how much gravity is pulling on that object's mass. And it is location dependent. So it says here, when the acceleration of an object is due to gravity alone, no air resistance, we say the object is in free fall. And we've studied that behavior already, because when you look at free fall, you're really not focusing on forces, you're focusing on the acceleration due to gravity, which is a kinematic property, right? Here we go with a new unit. So a new property, force. And so we have to understand the corresponding unit. Why? Because all of these properties are based on measurement. And anytime you measure, you need to be using a unit. And we focus on the metric system, the SI system, and the unit of force in the SI system is the Newton. Now they use a lowercase n here. Some textbooks will use a capital N to refer to Newton in honor of Isaac Newton. Okay. And then finally, Newton's third law. The third law deals with the symmetry of forces. In other words, Newton's third law helps us understand that forces exist in nature in pairs. And so let me read Newton's third law for you. Whenever one object exerts a force on a second object, each object experiences a force that is equal in magnitude but opposite in direction. So we can restate Newton's third law of motion in terms of action-reaction force pairs. For every action force, there is an equal reaction force that points in the opposite direction. Action-reaction pairs. Okay. So they show you this nice picture here of a swimmer. You know, this year's Olympic events, swimming was one of those things that was highly, successful for the United States, right? So what's actually going on there when the swimmer pushes on the wall with their feet? In terms of action-reaction pairs, the swimmer pushes on the wall with their foot. And you can see the red arrow pointing to the right represents the force vector for the feet pushing on the wall. But Newton's third law says, hey, if the feet push on the wall automatically pushes back on the feet. The wall pushes back automatically on the feet. How much? Same amount, opposite direction. And so this is how the swimmer can accelerate, right? They push on the wall pushes back and gives this forward kind of acceleration, okay? Now you might be tempted to say, hey, well, how can the swimmer accelerate? If they push on the wall and the wall pushes back and it's the same amount and they're opposite directions, won't they cancel each other out? We know from everyday intuition that is absolutely false. So the swimmer would never go anywhere, right? So something else must be going on here. And unfortunately, there are even some folk who are supposed to understand physics a great deal that miss this. The feet are pushing on the wall. The wall is pushing on the feet. They are not pushing on the same object. The only way you can balance the forces on an object are to look at the forces on that object. So what forces do we have acting on the wall? Let's take that object by itself. The only force we see there is the feet on the wall. There's no other force there. You know, there's some static friction. We don't see that label, but it's there. So that's why the wall doesn't move. But in any event, that static friction is on the wall. What about the swimmer? The wall is exerting a force on the swimmer's foot or feet. Yeah, because they'll have both feet in touch with the wall, right? Right, so the wall is pushing on the swimmer's foot. What other forces are acting on the swimmer? Well, the force acting on the wall is not acting on the swimmer. So when you draw a free body diagram to show the various forces acting on an object, be sure to take one object at a time and focus strictly on the forces acting on that object alone. And if you do that, you see we have to look at the swimmer and the wall as two different objects having their own unique forces acting on them. And so they can't cancel. So these forces that exist in pairs, these action-reaction pairs, they are the same size. They do point in opposite directions, but they will not cancel each other because they don't act on the same object. Okay, that's very important. The other thing that we need to understand, and this is simply from a perspective of being able to understand information that you're reading and utilizing, that there are different types of forces, okay? And we group those forces in categories depending upon how they relate to one another and the objects that they interact with, okay? So sometimes, you know, our common words, push, pull, right? Thrust, lift, drag, weight, friction, normal, and tension. These are all different types of forces that you commonly come across as you work through problems dealing with Newton's laws as you attempt to draw a free body diagram, okay? So these friction forces, these are any kinds of forces that act in opposition to the motion, okay? So it could be air drag, okay? Air drag is an example of friction. It is the opposing force that air exerts on an object. It could be static friction. This is the opposition force that works to keep an object from moving. Could be kinetic friction. Kinetic friction is the opposition force to an object that is in motion, okay? And a lot of times you'll see that friction is denoted or written in boldface lowercase f, right? Spring forces are sometimes, are sometimes indicated as well on an object. We're not going to focus on spring forces at this point. We'll have a whole section of material to deal with on periodic motion, and then we'll talk about the spring force and restoring type forces, okay? Normal force. This is a very important force, and we will try to approach it from a very straightforward perspective. Anytime two objects are touching, and the object you see as the dog food, I guess they're calling it Bow Wow Chow there, the dog food is in contact with the table. So the dog food is pushing on the table, right? The table is pushing back on the dog food. Another force that's acting on the dog food is weight, because gravity is pulling on it. So we want to take the dog food and isolate it. what forces are acting on the dog food. So let's draw a free body diagram there, right? So gravity pulling on the dog food gives it its weight, W, pointing down. The table pushing up on the dog food exerts what we call a normal force. So a normal force is a contact force between surfaces, okay? And it points opposite to the weight. That's the way we're gonna use it, okay? And so if the weight is W equals minus mg, then the normal force is opposite that, right? So the normal force as we're going to use it is equal in size, but opposite in direction to an object's weight, okay? And the other nice thing about the normal force and the weight is that they balance each other. So that's why the Bow Wow child doesn't fall through the table, because the weight force down is being balanced by the normal force up. Okay. Notice I am not focusing on any of the forces on the table. I'm focusing strictly on the forces that are on the bag of Bow Wow child dog food here. Okay. The weight of the dog food down, the normal force on the dog food up, and they balance each other. Tension. Tension is another type of force that you'll come across. And this is the force that is exerted by cables, ropes, chains, string, tension. And a lot of times is denoted with a capital letter T. Okay. So for example, in the picture, you see that there's this block with a mass M, and it's being pulled by gravity with a weight W down, and the rope is exerting a tension T up on the block. So now imagine collapsing the block into that dot that's on the right side. What forces are acting on the block? Well, the tension up, the weight down, okay? And so in the situation where everything's balanced, the tension and the weight are gonna be the same size, opposite direction, so the block is not going to accelerate as drawn in this picture, okay? But you see what they did? They represented the forces on that block in the free body diagram on the right by collapsing the block into this tiny dot. And notice the rope, it doesn't have any mass or anything like that. That's the magical world of physics. When we draw ropes, chains, pulleys, cables, we always say they're massless, they're frictionless. And these ropes, they allow the total amount of force that's being exerted on them to be transmitted to the object that they're attached to. So the hand is pulling with a certain amount of force T, all of that gets transmitted directly through the rope and to the block. You don't lose anything. In the real world, you'd have to take that into account, but not for our simple purposes. Because remember, we said early in the class, one of the things we do is model situations in a simplistic fashion as possible to get at the heart of what's happening, right? That's what we want to do here, okay? And then the last slide here talks about the 4 fundamental forces of nature. In nature, there are 4 fundamental forces. Gravity, which is actually the weakest force. The electromagnetic force, which is much, much stronger than gravity. The weak nuclear force and the strong nuclear force, okay? You can tell the approximate strength based on the size of the exponent. You can see that, you know, gravity is a very weak force on the order of 10 to the minus 38 compared to the, you know, electromagnetic force, which is on the order of 10 to the minus 2. And then you can see the weak nuclear force is 10 to the minus 13. And the strong nuclear force is given a factor of unity, meaning it's the strongest force, okay? So these are the 4 fundamental forces in nature. Now, we don't focus on electromagnetic weak or strong forces in this course. We focus on the gravitational force. And we can see that the gravity is an attractive force only, okay? All right, so, you know, that's one of the reasons why we focus so heavily on Newton in this course, because he gave us an understanding of how gravity behaves. And we'll see that later on, beyond our simple understanding that it produces an acceleration of 9.8 meters per second squared down on planet Earth for objects in free fall. All right, so that's what I wanted to cover there, okay? Let's take a few moments and see what questions do you have of me regarding anything I've covered in this particular packet before we move forward. Feel free, unmute and ask. All right, so what I'm gonna do now is I'm gonna go into the announcements, and I'm actually gonna pull these extra resources that I've shared with you, just to take a look at a couple of sample problems. And for those folk who've not seen this, if you go into the announcements, click on that extra resources announcement, here's the link that you can click on. And the nice thing here is that there is an actual folder for every topic that we cover, okay? And in those folders are some additional materials that you might find helpful. I don't mandate that you use them. You can get everything that you need from the notes and videos in the weekly overviews, but I like to pull from them because they have some nice, simple kinds of examples that reflect the kinds of things that I expect you to be able to do, okay, when it comes to problem solving. And it is exactly the kind of thing that you'll be practicing in the problem set. So it's not like if you don't use this, you won't get the practice. You will, because the problem set is you know, reflective of the kinds of things that you need to be able to do as well, okay? So let me go in here and find Newton's laws, and there it is. And so you see, I've got a whole host of resources for you there. Somebody had a question? Okay. All right. So this packet, Forces and Fluids, if you go out there, it's just informational. We don't really delve deeply into the forces and fluids in this class because you cover that in fluid mechanics, and some of you might even be in a fluid mechanics class with me right now, or if not, you will be, because I also teach fluid mechanics for the P-Tech program. Okay. This one that talks about Newton's laws is basically a restatement of Newton's laws. That's all, there's nothing else in there. First law, second law, third law, which we've already covered. How do you define force? Basically pushes or pulls, talks about balanced forces, unbalanced forces. And then it looks at, you know, Newton's first law, okay? So we've done that as well. But what I really do like is this packet that focuses on Newton's second law. I like this visual because it takes Newton's second law and rewrites it in the square so that you can see the, you know, as they say, the proportion, right? As F gets bigger, A gets bigger. As M gets bigger, A gets smaller. And then on the right-hand side is my famous problem-solving pyramid. You remember the whole goal of the pyramid is to what? Take an equation like F equals ma and represent it in a way that you don't have to know how to deal with equations. So if you want to solve problems that relate to Newton's second law, you don't have to use the equation. You can use this pyramid. How? Whatever you're looking for, cover it up and then look at whether you multiply or divide. If they're next to each other, you multiply. So if I wanted F I would have to multiply M and A. If I wanted M, I would have to divide F by A. If I wanted A, I'd have to divide F by M. So I only need to know how to multiply or divide to actually use Newton's second law in the way that we're going to focus on, right? It also reminds you of the units that are involved. Forces in newtons, okay? Masses in kilograms, and acceleration is in meters per second squared. And it reminds you how you make a newton. You take a kilogram, multiply times a meter per second squared, and you get a newton. Or you take a newton and you break it apart into a kilogram and a meter per second squared. So how do you make a newton or break a newton, which is important when you problem solve, because if your units are wrong, it's wrong. All right. So let's get to, oh, I also like this visual here, because it helps us to get an insight into free fall, right? We know what free fall means. No air resistance. Everything falls 9.8 meters per second squared. That's not your everyday intuition though, because you will probably have the intuition that elephants fall faster than peanuts. But that is because you are factoring in air resistance. So without air resistance, elephants and peanuts fall at the same rate on planet Earth, 9.8 meters per second squared down. But the question is why? Well, I'm sure, you know, hopefully it's not too late in the evening and you're not too tired, and you do recognize that elephants have a whole lot more weight than peanuts. They also have a whole lot more mass than peanuts. When you take the ratio of the elephant's weight to the elephant's mass, you get 9.8 meters per second squared. Likewise, peanuts have a lot smaller weight than elephants. Peanuts also have a whole lot smaller mass than elephants. But when you take the peanut's weight divided by the peanut's mass, you get the same amount, 9.8 meters per second squared. So it is the ratio of weight to mass that is constant during free fall, okay? When you factor in air resistance, then elephants do in fact fall faster than peanuts. And when you factor in air resistance, we can have a really nice, cool effect called terminal velocity. Why? If it's free fall, there is no air resistance. There is nothing to balance gravity pulling on an object during free fall. But when we factor in air resistance, the air resistance can balance out the gravity force. Okay. So as an object falls, it gets faster and faster. That's your everyday experience, even with air resistance. As an object falls, it gets faster and faster. But eventually, as it goes faster, the air resistance will get bigger. And as that air resistance gets bigger, eventually it will get big enough to balance the gravity force. So when an object falls in the presence of air, eventually the gravity force is balanced by the air resistance. Okay? And in that case, since everything is balanced, what does Newton's first law said? If all the forces are balanced, you don't have a net force, you can't do what? Accelerate. Why? Because you're moving at a constant velocity, constant terminal velocity. Okay? So it's when we acknowledge air resistance as a force and gravity as a force that we can have an effect like terminal velocity, because you'll keep getting faster and faster and increasing your speed and subsequently increasing air resistance, because the faster you go, the more air resistance you generate. But you can only do that until the air resistance balances out the object's weight or the gravity force. So when you fall with air resistance, peanuts do fall faster than elephants. I mean, excuse me, elephants do fall faster than peanuts. Yeah, right? So when you take into account air resistance, heavier objects fall faster, right? Why? Well, the elephant has a much bigger gravity force, so it needs a much bigger air resistance to balance it. If it needs a much bigger air resistance, it has to go much faster. So it will have a higher speed before it reaches terminal velocity. So in the presence of air resistance, elephants do fall faster than peanuts. Let me say that correct this time. All right. So now a few simple calculations that relate to Newton's second law. And why Newton's second law? Because with Newton's first law, there's nothing to calculate because there's no acceleration. No net force, no acceleration. The calculation comes in to using Newton's second law when you want to look at the relationship between force, mass, and acceleration. Okay. So in this example, we want to know how much force do you need to accelerate a 40 kilogram object by 4 meters per second squared. So they gave us the mass, gave us the acceleration. We want F. Cover up F with your smiley face, multiply M and A because they're right next to each other. 40 times 4 is 160. Kilogram times meter per second squared is a Newton. If you tell me 160 kilogram meters per second squared, I'm going to mark it wrong because you didn't properly deal with the unit. A 4 kilogram shot put is thrown with 30 newtons of force. What is its acceleration? So in this case, they gave us the mass, 4 kilograms. Let's say 44 kilograms, and a force of 30 newtons. They want to know what A is. So cover up A with your smiley face and divide F by M. 30 newtons divided by 4 kilograms. 30 by 4, 7.5. Newtons divided by kilogram, meter per second squared. How do they get that? Well, you take the Newton and crack it open into its parts and you cancel out the kilograms. So when you separate a Newton into its parts, you have kilograms on the top and kilograms on the bottom. They'll cancel and you'll be left with meters per second squared. And then the last one. This one is a little tricky, so pay attention. Not that I'm trying to trick you, but there is something to it that you need to be thinking about, is what I mean. Mrs. J weighs 557 newtons. What is her mass? So they gave us Miss J's weight, 557 newtons. That is Miss J's force. And they want to know what is her mass. See, the trick is anytime you know an object's weight, divide by the acceleration due to gravity, in this case, 9.8 meters per second squared, and you will get Miss J's mass. Okay, so according to the pyramid, if you want mass, cover it up with your smiley face and divide F by A. 557 newtons divided by 9.8 meters per second squared. It gives you 56.8 kilograms. How did I get kilograms? Take the Newton and separate it into its parts, as I like to say, crack it open. And then you'll have meters per second squared on top and meters per second squared on the bottom. And they'll cancel and you'll be left with the kilograms, okay? So let's see who's got their thinking cap on. All right, so it says, is the following statement true or false? An astronaut has less mass on the moon since the moon exerts a weaker gravitational force. Is this true or false? Somebody who thinks it's true, unmute and tell me why you think it's true. Okay. That must mean that Everybody thinks it's false. So somebody who thinks it's false, unmute and tell me why that's false. Anybody? Okay. That must mean that there are a bunch of people out here who don't know if it's true or false. So somebody who doesn't know, unmute and tell me, I don't know.
I don't know.
Okay, so now let's find out why. So it says, an astronaut has less mass on the moon since the moon exerts a weaker gravitational force. I agree, the moon does have a weaker gravitational force, but the mass of the astronaut does not depend on gravity. Remember, mass is location independent. It is the same no matter where you go. So it's false because mass doesn't depend on gravity. Your weight depends on gravity. So the astronaut actually has less weight on the moon, but the same amount of mass as they do on Earth. Okay, that help explain that? All right. The other last concept test that I want to share with you here is this one. And I put the answer right out there for you because the real benefit is understanding the explanation. So in the picture, you see this block, and there are forces acting on the block. I don't know if I can't, let me see if I can zoom in any. No, maybe here. Let's see if I can zoom. Yeah, there we go. That's a lip. Oops. Let's go down. Bear with me for a second. I want to get it. Yeah, so that's a little bit better of a visual, right? So you see there's this block, and there's a normal force, 20 newtons up, and there's a gravity force, 20 newtons down. So everything's balanced on this. Okay, that much we should be able to agree on. 20 newtons up is balanced by 20 newtons down. The question is, does this object have to be at rest? And the answer is false. It does not have to be at rest. Why? Because a net force does not cause motion. A net force causes a change in motion or acceleration. So this object could be at rest. That's one possibility. Or this object could be moving with a constant velocity. That also means the acceleration is zero. Right? At rest, we get it. There's no acceleration because it's not moving. But it could be moving with a constant velocity. That also means that the acceleration is zero. Okay? Remember, net forces don't cause motion. They cause a change in motion. And that change in motion is what we call acceleration. So what do you have to have present if you want an object to accelerate? A net force. Do we have one in this picture? No. Then the object cannot accelerate. If it can't accelerate, there are two options. It's at rest or moving with a constant velocity. Okay? So that's the nice thing about these, this extra notes that I've made available to you. There are always some great insights there, okay? And you can go and take a look at those extra notes. What I want to do now is I want to talk about your bonus, and then I want to talk about the midterm, okay? So right in the Newton's laws overview for this week, there's a link to your first bonus, okay? So this first bonus actually deals with 2D motion, okay? It deals with circular motion, and it's worth 10 points toward your midterm score. So 10 points. 10 bonus points toward your midterm score. All right. And so what you have to do is you have to go out to this website. So let me open it. And this is NASA-sponsored website on the International Space Station. If you recall last week when we did the example, which goes faster than Neo or the Leo or the Geo, I mentioned the International Space Station as an example of a Leo. Okay. And so I want you to come out to this NASA website that deals with this International Space Station. And I want you to use the website to help you answer these 2 bullet points. Give me a brief description of something that you learned about the International Space Station from the website. And then use the locator tool. One of the things you can do on this website is a locator tool. Use that locator tool to tell me when the International Space Station is going to pass over your hometown or the closest city to you. Okay, those 2 things. You go to that website, you answer those 2 things for me. You turn it in, according to the deadline that I published here, which is this Saturday, right? If you look at the, sorry, let me scroll up a bit here. You look at the activities, your first bonus is due this Saturday. You go out to that website, answer those 2 bullet points, turn it in just like you do any other thing, any other assignment, and I will look at it, score it, and put your bonus points on the side so that when I score your midterm, I will add it to it. Okay, first bonus. Any questions on that? Okay, no questions on that. Let's go back to the weekly overviews. All right. And if you notice, here we are this week, week 6. Next week, week 7 is your midterm week, okay? So it tells you here, when you click on that overview, your completed midterm is due by 11:59 p.m. on Saturday, 9 October. Please follow the Honor Lock Canvas guide to have your exam proctored, okay? So, sorry. Right here's the Honor Lock Canvas guide. So you can use that to help you prepare to, get your exam proctored. You should try to practice exam first. It's not for any points. It's just to walk you through to make sure that all of your things that you need for the exam are working properly, like your camera, you have your ID, you have the Honor Lock extension installed on your machine, that kind of thing, all right? So try to practice exam first. When you are ready, then you click on the Honor Lock link to the left. Notice it's here on the left menu, and it'll take you to go to the exam. If you try it now, it's going to tell you it's locked because it doesn't open until Saturday. It opens Saturday, okay? But I won't see you on Saturday, so I'm going over this with you now so that when Saturday comes, you'll be ready to take it. Now, there are fees associated with proctoring that was covered in the syllabus, that's covered under course documents. Has been out there since day one. So when they ask you to pay, choose the $27 option because it'll save you a few bucks because you only have 2 exams in class, right? Midterm and a final. So $15.50 per exam is like $31, but they give you a little discount if you tell them right up front that you're doing both the midterm and the final. Okay. All right. There is a study guide. I'll talk about it in just a moment. I've kind of synthesized the directions for you here in this link that says exam logistics. This is available. You can come out here and take a look at it now. The only thing you can't actually access is the exam itself right now, okay? But everything else is open and available, all right? So it tells, I explain my logic for giving you to these 2 formal exams, midterm and final. You can use any printed resources that you choose, including textbooks and formula sheets. You can use a calculator. You are not allowed to use a phone, tablet, or any other website. And that information has been passed along to Unlock, so they know what you're allowed to do, what you aren't allowed to do. Okay. I'll remind you of the due date. I give you an overabundance of time here, 4 hours to do the midterm exam. Okay. It is proctored by Unlock. And the directions for using Unlock are in the Unlock Canvas guide. There's another link to it in case you need it. I explained the fee structure again, so it's in multiple places. All right. Type your work in the exam space provided. You must show your work to receive credit. No credit will be given for correct or incorrect answers if work is not shown. Make sure to follow all instructions included with each problem. Please do not email me your work. Type your work in the exam space provided. Okay. Midterm is worth 100 points. And, if you miss the midterm, then we have to talk about, makeup and documentation and what have you, things like a doctor's note, obituary, judge's order. I know, some folk are still experiencing some issues. So we take that on a case-by-case basis and work through it, okay? All right. And then the study guide. So the study guide tells you the areas that the exam focuses on. Notice there is nothing on Newton's laws on the midterm. The midterm topics ended last week. Okay. So the stuff we covered today is not on the midterm. All right. Again, it tells you use any source of your choice to find conceptual information and sample problems that relate to the topics listed above. Okay, so you are going to go on a quest to find information that relates to these topics. You can use books, internet sites, or any other credible sources, right? For practice and for points, you should list 10 concept facts, okay? And I put one here that deals with Newton's laws, but again, Newton's laws is not one of those topics. I was just giving you an example there, okay? So you want to list 10 concept facts that relate to these topics and solve 10 problems. And you can pull those facts from textbooks, from websites, those problems from textbooks, from websites, any other sources that you like to use. You should have a total of 20 items, 10 concept facts and 10 problems. Not 10 concept facts and 10 problems on each one of those areas, 10 concept facts and 10 problems total. But you don't want to do all of them on one topic. You need to spread it out, right? So you should deal with more than one topic, right? So don't solve all your problems and concept facts on projectiles. Spread it out and do some on each one of those, okay? Any examples in my lecture notes, you're not allowed to use it, but you can use the extra notes that what we looked at today, the extra resources. You can use anything from those resources under useful links. You just can't use my examples that are in my lecture notes, the supplemental notes, okay? All right. And you must turn this study guide into me by email, okay? And it's due the same time that midterm exam is due. So not this Saturday, the 2nd, but October 9th, about 11:59 p.m. So you have to have your exam completed by then. You have to have me the study guide by then if you want these bonus points. And this is worth 10 bonus points toward the midterm as well. So you have an opportunity to earn 20 bonus points toward the midterm exam just by completing the study guide and the bonus on the International Space Station, okay? So what are your questions on the study guide, the exam logistics, or anything else that you might want to ask me about the midterm? Okay, Well, if you're working on anything for this week, whether it's the assignments that are due Saturday, or you decide, to jump into the study guide or the midterm exam this weekend, I will answer any questions you have about the problem sets that are due, the discussions or anything like that. But I will only answer administrative and logistical questions about the midterm. I will not answer any physical science questions about the midterm. Okay. At that point, you decide to take the midterm exam, you need to be comfortable with the physical science that relates to those topic areas, because I want to answer questions about that. All right. Anybody need to ask me any questions before we call it a night?
I have a question.
Yes, sir.
Do you,
Please.
do you turn in the bonus and the study guide on your email?
Yes,
to your
just like
email?
just like any
Oh.
other assignment.
Oh, all right. Cool. Thank you.
This all has to be turned in like before the exam or the same day as the exam?
The bonus on the International Space Station is due by this Saturday. The study guide is due by the deadline for the midterm, and those dates are explained there in the overview. Anybody else, please ask. All right, so I'm going to stop the recording. And